So today we're going to be talking about gravitational waves and their discovery at Ligo. So let's go ahead and get started with this. So this is the actual paper that came out of the discovery of gravitational waves. And this was a really big deal. So much of a big deal that when I was in graduate school, all of us were getting around a computer in order to watch the announcement of this discovery live. And it wasn't just a big deal for all of us physics nerds, it also then won the Nobel Prize. So, Rainier Weiss, Barry Barish, and Kip Thorne all earned the Nobel Prize for their work on discovering gravitational waves. So let's talk about what gravitational waves are to begin with. But first, in order to do that, we need to figure out what this whole general relativity thing is first. Then we're going to talk about LIGO, what the Nobel Prize was actually awarded for, what's happened since, and then a little bit about the future of gravity wave detectors. So, Einstein's general theory of relativity. Don't worry, this won't be on the test. So, one of the analogies that's used a lot is you have a rubber sheet, and whenever you put something heavy on that rubber sheet, that is going to then deform, and the heavier objects, the more deformation you're going to have. So basically think of this being a big divot in our rubber sheet. And then you can imagine that now you have this funnel in the rubber sheet, and as things move across that rubber sheet, it's going to then get stuck going around that funnel. This is the way gravity works in the general theory of relativity. Is essentially you have mass that's deforming the space-time continuum, and then that deformation, that change of shape of space-time, is what then gets other objects stuck in it. So, a coin is stuck in a funnel as well, just like this. Put the quarter in and watch it spin around like crazy, and then you make your donation. The moon is stuck in Earth's gravitational well. The Earth is stuck in the sun's gravitational well. The sun is stuck in the galaxy's gravitational well. And black holes are just large enough gravity wells that light itself is stuck in it. You have to be going faster than the speed of light in order to escape. So you have light orbiting the black hole, and because it's orbiting rather than escaping, that's why it's a black hole. Light doesn't get out. And also, that's why nothing can escape, because light's the fastest thing there is. If you can't go faster than the speed of light, no way to escape the gravity in a black hole. Star Trek is perpetually wrong on this. Yeah, I know, I'm sad about that too. So, what are gravity waves? So let's go back to our rubber sheet analogy. So when an object accelerates on this rubber sheet, and acceleration is the change in velocity, and velocity is a vector, so that means that anytime you have the direction changing like you do in a circular orbit, that's an acceleration, and it creates a ripple. So you can imagine, back to our rubber sheet, that you would have two bowling balls on this rubber sheet, and these objects would be orbiting, and therefore that would be causing the entire sheet to vibrate, and you holding on to the edge of the sheet could then feel that vibration, and that's essentially what we're dealing with here. So so objects orbiting makes the rubber sheet. Objects exploding could make gravity waves, think supernovas. And then the biggest explosion there was the Big Bang, and that would also then make gravitational waves. So, this cartoon is a great one because, I mean, yes, I just used the rubber sheet example. And that then distorts things. But whenever you have a whole bunch of physics nerds getting together, it's like, how do we make this analogy better? And the answer is we haven't come up with any. But we could also then just talk about the math rather than the analogies, but that just gets ugly. But we're going to look at it. We're not going to deal with it, but we're going to look at it. The math is really, really hard. So, this is Albert Einstein. He had the annus mirabilis, which is Latin for the miracle year. In this year, he wrote 4 papers that completely changed physics. And by that I mean each one of these papers completely changed physics. He came up with the photoelectric effect. So this was what he then earned the Nobel Prize for, and started off a lot of quantum physics. He came up with Brownian motion, which was the way to explain how atoms and molecules bump into each other in air or in water, and how diffusion actually happens. Special relativity, so how objects act when they're going near the speed of light. And then also his famous equation, E equals mc squared. That was all in 1 year. And the math is hard. The math is really, really hard. It took Einstein 10 years to figure out the math of general relativity, and he almost gave up many, many times. And he had to get help from Max Planck, who was sort of the genius, mathematical genius of his time. So he was the Einstein of Einstein's day. And if you look at the equation there, it's complicated. It's like really complicated. It's to the point where the math no longer looks like math. This is multivariable tensor calculus, which is something that's difficult to pronounce, yet alone actually do. So this is the equation for all of general relativity there. Luckily, there's ways to solve it and make things happen that we can look at, and we can actually understand that, hey, look, that looks like math, and then actually have something that we could maybe solve. All right, so one of the things about waves is they carry power. And all orbits radiate gravitational waves. So this means that all orbits are unstable because there's a little bit of energy going away from it. And I got the equation there. So this is the equation for power. So power, the power that's radiated away from the gravitational waves. So the amount of energy that's lost by these gravitational waves for something orbiting is 32/5 times some constant. So that's the gravitational constant to the 4th power divided by the speed of light to the 5th power, times the product of the two masses squared, times adding those two masses, and then you take the distance between the two objects to the 5th power. This is still a really ugly equation, but it's something that I can plug into my calculator, and once I do plug it into my calculator, I can find that for the Earth and the Sun, the amount of power that's radiated is a whole 200 watts. So that is less than what's being used right above me. So we don't have to worry about the Earth spiraling into the Sun anytime soon. In fact, the amount of light coming off of the Sun beating into our planet pushes our planet off way more than we need to worry about our orbit degrading because of these gravitational waves. So, the Nobel Prize had already been given for the discovery of gravitational waves. Just they did it in the looking at energy rather than actually detecting the waves. So in 1993, Taylor and Holtz were looking at a pair of pulsars. Now, pulsars give off light at very distinct pulses, and they are actually the best clocks in the entire universe. But when looking at these pair of pulsars that were orbiting each other, they noticed that they were slowing down. That meant that they were losing energy. And when they calculated the amount of energy lost, the masses, they found that it all matched. So that means that mathematically they were able to show that, hey, look, the system is losing energy, and the amount of energy that the system is losing is exactly the same as what would be for gravitational waves. So we already had a really good idea that these things existed. We just hadn't been able to measure them. In fact, for most of my being interested in physics kind of time in my life, gravitational waves were always one of those things where, yeah, we'll never be able to measure it. It's so small. That is why this is such a cool thing, is we actually did it. All right, so gravitational waves compress space, but only by a tiny, tiny, tiny amount. So the equations for how much it compresses space are in the bottom right-hand corner there. And you can see that it's like nothing. In fact, it's 1 part in 10 to the 25th. So that's 1 part in a 1 followed by 25 zeros, which is way bigger of a number than I know how to pronounce, other than it tiny. So this is way, way, way smaller than anything else that we've seen in the universe. So, what is LIGO? LIGO is something that measures this compressing of space. So, it stands for Laser Interferometer Gravitational Wave Observatory. And there's 2 different spots that they've got this set up. There's one in Livingston, Louisiana, and there's another one in Hanford, Washington. These are 3,000 kilometers apart, or 0.01 light seconds. That means that if a gravitational wave comes in, and they're moving at the speed of light, there's going to be a slight time offset between the 2 observatories. And that way you can determine that, yes, if you're measuring one at one location and the other at the other, you can say, yes, it came in, we detected it at both spots, and it was offset, so we know that it's someplace over in that general direction. So what is a laser interferometer? When waves overlap, they can add and subtract. And you can see this when you go to the beach, or when you look in a pond and drop 2 pebbles next to each other. Those waves, as they go out, are going to overlap. And this happens even when light waves. So what we've got going on here is that a laser is split and then goes down each of the 2 arms, which is 4 kilometers long. And then the beams are then recombined at a photodetector, and this is sensitive to 1/1000th the size of a proton. So this is way, way, way more accurate than I can understand how they did it. But they were able to engineer this and pull this off. How this works is you have a laser that then fires down at 2 mirrors, and as those mirrors bounce back and forth, like what would happen if a gravity wave were to come through, it would then hit the mirror. So here we see that laser light coming, getting split off, and then coming down and hitting this very precise mirror and bouncing back. Those 2 waves are then recombined and then come together slightly out of phase. And so they're essentially canceling each other out. So as the mirrors move back and forth, they go in phase and out of phase, which affects the brightness. So that can then be detected on this detector as it goes bright, dark, and that is how they are able to make the most accurate measurements of just how long. One of the keys to all of this is, how do you hold the mirrors so still? Because any vibrations in the mirrors is going to throw off your results by a lot. So one of the keys is to isolate the mirrors. So the mirrors are then put on several pendulums, each pendulum being very, very massive in order to keep it from moving. And then they've got something called a beam recycler. So that sends the beam down the tunnel many, many, many times. This is essentially taking many, many measurements and averaging them together in order to get better results. And then they have other fancy things like active seismic stabilization. Basically, they have motors to move the anchors just a little bit in order to counter any earthquakes or UPS trucks driving by. And then they have one of the best vacuums on Earth. So there is less particles in their vacuum than there are in the vacuum of space. So it's a very, very empty area in order to keep random molecules from interfering with the laser light. So the detection. At 9:50 in the morning, well, this would be Greenwich Mean Time, a signal was detected both at Livingston and at Hanford. And what you've got over there on the right is the waveform. Basically, it's what the wave looked like if you were to graph it. And this very, very carefully matched what was predicted, both in frequency, basically how close together the lines are, and the amplitude, which is how big up and down the lines are. And the data is noisy, so it's jumpy, so it doesn't match exactly. But you can see over on the right how the data, which is the darker orange line or the thicker orange line, or blue if you're looking at the other graph for Livingston. So that's what was measured. And then that thinner line is what was predicted by their computer simulations. But if you take the noise out just a little bit, it matches what was predicted very, very well. In order to figure out what the collision was actually made of, what they essentially did was they modeled in their computer a whole bunch of different collisions of black holes. They took black holes as small as the mass of our own sun, all the way up to 100 times bigger, and ran all of those simulations to figure out what they would look like. And then what they essentially did is they taught the computer, hey, look, this collision looks like this collision looks like that. And therefore, the computer was able essentially to learn all these flashcards and then identify what these collisions would look like. It was just too complicated to have the computer work backwards. So take a look at the waves and then figure out what the collision was. It's just a lot easier to then match it with simulations. So they did this, and we've got about 10% uncertainty, because as precise as this equipment is, there's still a little bit of noise in that data. You might remember that from looking at the wave graphs. So what was the black holes that we got? So the primary black hole was about 36 times the mass of our sun, or 36 solar masses. And the second black hole was also really, really big, 29 times the mass of our sun. And then these combined to make a final black hole at 62 times the mass of our sun. So really big. Now, some of you are looking at these numbers here and going 36 plus 29 does not equal 62. And you would be right. That's just the thing. In their collision, some of that mass was converted to energy thanks to that E equals mc squared equation. And in that collision, and with that mass loss, this actually was more powerful than the rest of the entire visible universe when it was colliding. So a truly, truly massive amount of power given off by these colliding black holes. So much so that it deformed space itself, and we were able to detect it here on Earth, billions of light years away. And that billions of light years away is indicated by that redshift down at the bottom, and that basically deals with Doppler effect and distance and things like that involving with an expanding universe, but that is a completely different topic. So let's see this detection again. So we've got that collision being 3.6 times 10 to the 49th joules. So essentially, that's getting rid of a huge amount of energy. That's essentially burning through 200 times the mass of our sun every second, but it happened for a very, very brief time. So this was 1,000 times more powerful than the entire visible universe. So I'm sorry, 10,000 times more powerful, but only for a very brief period of time. Something on the order of 5/100ths of a second, but still very, very impressive. So here we have a video of the two black holes coming together. And pay attention to the time up in the upper left-hand corner, as you can see that this is way, way, way slowed down. The waveform that's being generated down at the bottom is what is then going to be picked up by Ligo when it gets to there a couple of billion years later, because it's that far away. So these are spinning around very, very, very quickly. They are orbiting each other at, as near as makes no difference, the speed of light. So they are getting closer and closer, and the distance between them right now is about the size of a large city. So you can see that now we've slowed down time even more in order to show just how much space-time is being ripped apart right at the point of merger. Here we've got those two event horizons merging, and as soon as that happens, everything goes to dull. The event is over. So it was very, very violent for that split second, but now, as time speeds back up, there is nothing, and all that is left is just one giant black hole sitting in space. So where did this occur? So there's a bunch of things going on here that mean that it's very difficult to figure out where in the universe that this occurred. However, we've got a map. This is the banana graph that shows where in the sky it might have been, and we can figure that out based off of the timing of the events that occurred in Louisiana and in Washington. So this is a map of the night sky. I've got some of the stars labeled here. So Orion in the constellation is up in the upper right. We've got Sirius, the dog star, following that. And Sirius is the brightest star that we can see in the northern hemisphere. Then you have some southern hemisphere stars like Eta Carina, which is the brightest star in the night sky, and one that I would very much like to see someday, but I have not been to the southern hemisphere. And it's somewhere in that plot. So we're 90% sure that it's someplace in the purple, 50% sure that it's somewhere in the green, and then less sure as it's going in, but that's our best guess. So someplace in the southern hemisphere is essentially what we've got as far as location. And then we've got the small and large Magellanic Clouds, which is another thing that I would eventually like to see. So why is this so important? So this opens up a huge new area of astronomy. So it's one of those things where galactic mergers occur. In several billion years, our galaxy is going to merge with Andromeda. And that's not something that we really understand, but with looking at gravitational waves, it'll give us another insight into that. It's also going to be huge for black hole astronomy. It already has been. 30 mass black holes were thought to be very, very rare. But yet, here we had two of them colliding into each other. So this leaves a big question in our understanding of how black holes form, how often they merge, and a whole bunch of other questions that we need more data in order to figure out. This is also really big for neutron star astronomy. Since this discovery, we've discovered a couple of neutron stars colliding. This is really important because neutron star collisions is what gives us a lot of our heavy elements, like gold and other uranium and other things like that, is very critical for daily life. And all of those are born in the collision of neutron stars. It's also going to be very important for our understanding of the early universe. At the beginning of the talk, I mentioned that the Big Bang itself spawned gravitational waves. This might give us a chance to detect some of the stuff that was going on very early on in the universe. This is because we can't see that far back. The furthest that we can see back with our optical telescopes is something called the cosmic microwave background. It's essentially a curtain that was drawn at about 300,000 years into our universe. Because prior to that, the entire universe was glowing like a star, and we can't see past that curtain. So gravity waves might allow us to do just that. So let's talk a little bit about the future of this, and then we will get going. So finding something opens up the taps for funding. That's just the way that science works. The money goes where the success is. And now that Ligo has been successful, the money is starting to flow. And several more LIGO experiments are opening up over the world. So right now we have one in Hanford and one in Livingston, so that would be Washington and Louisiana. There's another one that is now active in Northern Europe, up on the northern border of Germany. There's another one that's going to be, is being built in Italy. Another one that's being built in Japan, and there's one that's currently being planned in India. With all of these detectors, we're going to be able to be much better at finding them and then determining where in the universe these occurred. Also, we can put one in space. So this is something that the Europeans are working on. So LISA, or Laser Interferometer Space Antenna. So this is a project that was originally designed by NASA and Caltech and JPL, but they basically said, no, we're not going to fund it. So luckily, a lot of the design work was already done, and it just needed to be built. And the European Space Agency said, okay, we'll build it if you don't want to. So it's going to be 3 satellites that are going to be have about 5 million kilometers between them, and it's going to have similar abilities to measure as the ones here on Earth, but because there's no earthquakes, because there's no UPS trucks driving by, because there's no vibrations out in space, it's going to be able to be much more sensitive because it's not going to have all that noise going on. So you'll be able to look at it and go, yes, that is a collision of black holes, or not, and much easier. And the prototypes for that is already launched, and it looks promising. With that, they won the Nobel Prize for it. And it's a very exciting area of physics that only more is coming out. So watch this space. More things about our universe are being discovered every day. With that, I wish you the very best of days.